beautiful mode. All right, so let's recap a little bit, right? See, there's a long, rich history, right? Started about 250 years ago. How to do estimating, predicting a signal, a data points, and by fitting with a linear or multiple linear functions, right, against it. Start with the simplest case, right, fitting the data with a single linear function. And of course, the error can be Gaussian noise, dense Gaussian noise, or sparse corruptions, right? You can do L1, L2, right, solving. And in some cases, L2, you have closed form. Many of the cases you don't. You have to solve this numerically. Sometimes the problem become even if you put some restriction on how many number of components you can use, right? Regressor you can use. The problem even can become from starting from having closed form solution in the case of least square to the case that is intractable. Okay, and then people solve this using very brute force techniques. Okay, in early days, right? And later on, they're relaxing them with L1 minimization and so on and so forth. That's very popular in 1990s, and leading to the compressive sensing, right? How to solve this class of L1 minimization in a very systematic way and help us understand high dimensional geometry, even starting from this simile-Bilal class of problems, understanding the relationship between polynomial and P equal to NP in a much, much better way. Okay? And also understand a little bit deep networks, right? Turns out that this family of knowledge is very important for us to understand because it helps us understand the low-dimensional structure in high-dimensional spaces, at least for important class of low-dimensional structure. Hence, some of the phenomena generalized to even other low-dimensional structures, which we will benefit a lot in our course, in our understanding of deep learning. Okay, that's the purpose of this course. Now, of course, in parallel, people also solving the least square fitting problem in a more special setting where the data is the causal, is time series. Okay, so they're not generic vectors. They're not the very idealistic case like before. In the engineering setting, usually we're dealing with data are time series, right? They're causal, they're in time. They have some special structures. In this case, the least square estimation takes special form and also special solutions. And in the case under, again, very Bilal conditions, at least for the linear time invariant case, the denoising filtering takes closed form solution, right? This is in a spectral, here I just for simplicity express this in the frequency domain. In the time domain, just read my book, right? The appendix of the old book. And also in dynamical systems, again, the least square fitting, right, against the linear dynamical system, the least square fitting, again, solving the minimum least square problem, leading to a beautiful recursive solution takes the form of Kalman filter, okay? Again, this is, I cannot overemphasize the importance of this. Anything, people actually use this to estimate anything dynamical, either linear time invariant, nonlinear systems, okay? There's the Kalman filters is very, very popular. And so far, right, all the things assume we already know the system, we already know the regressor, we already know the system parameters. But if you don't, then you have to only use the input-output to identify the system, right? Again, using the fact that if the system is linear, then all the state, right? You should identify what is the subspaces that the system sits on, right? All the observation sits on, right? And that because that's the key to estimate the ABCD, identify, make the black box into a white box. And of course, in general, right? The system, in general, we have data. We try to identify where the subspace the data lies on, right? That's the general PCA problem. Again, this is a problem that has been studied like crazy by, for 100 years. Many famous mathematicians works on it, right? How do you learn both the regressor U and the coefficient W simultaneously, okay, for all the data. And this problem, as I said, there is a geometric formulation of this problem, right? Geometric formulation is find a subspace so that all the points, the arrow projected on the subspace, the arrow gets minimized. This is the geometry. And there's algebraic formulation, which is viewing all the data points as a column of a matrix, try to fit this matrix, approximate the matrix with the matrix of rank no more than D. Okay, this is called the low rank matrix optimization problem. And also, of course, many years ago, there's a pure another formulation by Bastrami and Jordan that this is actually doing this. But anyway, this problem in this particular setting has a closed form solution given by SVD, right? But this is a single subspace. What if you have a multiple subspace, multiple components, and the sense gets a little bit complicated as ICA or generalized PCA. And the diction learning is a special or generalizing or unifying way to look at the ICA or generalized PCA. And also that it turns out you can actually solve the optimal denoising problem even without identifying. If you only care about denoising, okay, only care about the Gaussian noise denoising, and it turns out you don't need to know the identify the support of the ground truth distribution. You only need to know the empirical distribution, the density of the ground, the empirical distribution. Then you can already, by taking its gradient, you can already do the denoising in an optimal fashion. Right? Hence, you can, in order to identify the distribution, you can add the noise, make it increasingly become random, and you can learn the denoiser, right? Make it increasingly converging on the ground truth distribution. And in this process, diffusion increase entropy, decrease in denoising, reduce entropy, right? So if you apply, this is example that I've been mentioned, right? If you apply this to a one-dimensional distribution, this is what you get, right? Get something boring, but if you apply this to a distribution sits in the thousands or billions of dimensions, things gets very interesting because you can actually use the denoising to learn to get access to the distribution of natural images, to generating natural images. Generating image looks natural, okay? Natural object, natural things, so on. All right, but here I kind of, as I said, I bury something, right? How do you know this guy? Right? This relies on to compute the gradient, right? In order to do the denoising, guys, relies on to compute this guy, right? See here, I have the empirical distribution. I need to compute this guy. But this guy, what is the expression of this guy then? Right? Do I have to evaluate this at every point? Then I cannot have anything structured, right? So remember, this is empirical distribution. Well, what the heck is this guy? How do I approximate? How do I compute this so I can do the gradient descent in a very efficient way? That's what the neural network is doing, okay? Even the diffusion model, right? The denoising model, I mentioned this, right? People just use the diffusion, using a transformer or using whatever, convolution neural networks, UNet to implement this, right? To implement this. So hence, there's a very rich history in the practice of neural networks to approximate this kind of compression or denoising operator, okay? You use deep neural networks, right? Inductive design, right? Trial by error, right? Here is a history, right? I do a very quick recap. You should read the chapter 1, you get a much full picture, right? Started in 1948 and derive a model for the single neuron, and people start to build the perceptron, 1950s, after that. And so this is the article, right? You can see the New York Times, right? 1958, electronic brain teach itself. So as I said, 对吧？我们今天吹过的牛，那个时候都吹过了，对不对？你看上面写的什么 ？It's so much like a human without life, and also there's the perceptron believes that it said that it needed the device to hear speech in one language, and be able to understand language and writing it, another language, translation, and the machines start to become conscious of their existence and literally teach itself to recognize the object the first time it sees them, counters them. And then they may believe that it's building a thinking machine that will be able to read and write. All right, guys. There's many articles like this, okay? 就是也是一样啊，就是要么就是大家不用工作了啊，这个 machine can think, machine can do anything, can learn, can speak all languages, okay? And take over all jobs, okay? 这个become conscious， 这是无几点啊。所以我们说过嘛，现在吹过了牛，那个时候都吹过了，对。而且 the techniques 都一样，对吧 ？It's very much the same networks as it's a smaller, right? It's a 大概500个节点的perceptron MLP, okay? Of course, it didn't work, right? It spent about IBM 花了大概200万那么 Navy 也花了好几百万 ，OK？ 最后 of course didn't work, right? Then of course people become humble again. 1980s, Fukushima proposed the neocognitron, proposed the convolution neural networks with Renu. Yan LeCun again in the Bell Lab spent a lot of money to implement LeLet, which is the predecessor of AlexNet, right? 2002. Then people after that, of course, this cluster of development is faster. After 2012, AlexNet, ResNet, Transformer, GoogleNet, VGG, and all the other. Then GPT-4, 5 come out, right? 但是大家知道啊，大家这些做的本质上是一样的东西，只是在 scale up，OK？ 所以58年吹的牛，5几年吹的牛啊，跟现在吹的牛是一样的，因为大家做的事情都一样啊，网络结构也差不多啊，只是 scale 更大一点啊。So of course the scale matters, right? So this is a transformer. I mean the scale matters. The dimension gets higher, right? Image usually the tens of thousands of dimension, and these the feature space is much higher dimension, capture much more details. The distribution, the sample gets large, right? We usually have billions of samples, right? We have billions of points on those distributions here. Can guide to learn those diffusing model, to learn those denoising model, right? To learn those operator better and better, to estimate those empirical density more and more accurately, right? Again, but those operator, we use neural networks, right? And then of course people try 谢三林, right? Those guys try DIT, diffusion transformers, to realize the denoising compression operators, or realizing those things. And actually Sora is very much used DIT, right? Those are the results from Sora, and this is about a year ago. These days probably gets better, 对吧？所以红色的都是用这个，还是用这种 trial and error 的 empirical neural networks 实验，包括 GPT-4、GPT-5， 对不对？包括 Sora 等等都是这样的。So can we do this analytically? The question is, 对吧？你看现在，看传统的我们做去噪。Traditionally in classical signal processing, data analysis, and high-dimensional geometry, and so on and so forth, we actually compress system. We actually try to denoising against a analytical model of distribution, right? Mixture of subspace, Gaussians, or at least do this in a principled way using Twitty's formula, right? Using estimating the density or gradient of the empirical distribution and try to approximate it. So this is the practice, is that we actually have to approximate these operators using some architecture, right? So, but can we actually combine this? Can we actually design neural network layers to realize the denoising compression? Can this be designed in the analytical approach? Yes, you can. If you know the distribution P, if the P can be modeled analytically, right? If we approximate the PX with a mixture of subspace or low-dimensional Gaussians, either as PCA, ICA, GPCA, sparse coding, and so on, then you will see, right? The operator, this operator looks like this. It starts to look like what? Transformers, right? So you can, as long as we can model the the distribution of the data in some or approximate them with some analytical model, then those denoising operator becomes analytical. It takes very special forms, can be implemented very quickly, right? So then how do we do this? We know, right? If this operator reduce entropy, right? So entropy in information theory directly associated with the so-called coding length. Entropy is actually the distribution if you choose the optimal code book, and then the entropy is exactly associated with the length of the code book. If you have enough data, right? Very large data sets drawn from this distribution PZ, right? Hence, the coding length or coding rate, to be some, or I should take an average here, should be coding rate, will be exactly associated with entropy of the distribution, right? So then if a distribution is truly low dimensional structure, has the support is low dimensional, then the entropy should be very low, right? Should be highly compressible, should have a very small coding length, entropy. Therefore, in order to find this distribution, right, we can actually try to find a code book such that the coding length gets lower and lower. Right? 如果尤其是 if I can approximate the distribution such that the coding length can be measured in analytic form, we'll teach you how to do that later, right? If the distribution of the data, the coding rate or coding length or the distribution P can be approximated by some analytic form, then maybe we can minimize it. Then we can actually conduct a gradient descent to minimize those coding rate, to reduce the entropy, right? We can compute this in analytic form and reduce the entropy. Make it converge to the low dimensional structure. So that's the idea. So hence, our job, if we wanted to understand deep networks, if we wanted to compress data correctly, if we want to do this analytically to derive design neural networks, right? We need to have an analytical form for either the distribution itself or the coding length, coding rate associated with this distribution. Hence, we can reduce it incrementally, right? Make the codebook better so that the entropy gets reduced. We'll talk about this in a second, right? Hence, then if I can find the expression of L, take the gradient, then I do this iteratively. So 就跟那个 gradient descent 就是吧，我在这里对吧？开始的 coding rate, coding length is larger. I take iteration and so on and so forth. Then I can view all this iteration, the gradient as consecutive operations, 对吧？我就重新取个名字。This gradient descent operator as a layer, right? First iteration, second iteration, third iteration, L iteration. And if I concatenate these operations, this really become a sequence of layers, right? This naturally give you deep networks. And also each layer is precisely conducted to realize this gradient descent operator. It's doing denoising, it's doing compression. Okay? So in this course we'll learn, right? Yes, you can. Only thing you have to find a way to analytically measure P, about P or L. Once you do that, you can derive, right? So now this really allows us, you can see on the left, right? The ResNet, ResNext, right? This is a mixture of experts. This is the transformer, right? So you can see once you do this, you can actually, you can design completely new architectures entirely. So instead of all the empirically designed neural networks architectures, while trial and error, right? This is a really inductive way to derive those neural networks. It takes years, many teams, many trials, right? Many tweaks, many hyperparameters, many trial and error of hyperparameters, architectures, and diagrams, and so on and so forth, right? Now, you actually can derive, right? From analytic form of P or L, you actually can derive what the network architecture should be if they do the denoising, do the compression, and do the gradient descent for you, right? So here is what we'll learn in chapter 4, right? Using this principle from first principle, right? How do we measure a distribution's density or the coding rate to do a very good approximation in a principled way. Then we actually can optimize, compress the data. Right? You end up with architecture we call the ReduNet, rate reduction network, or this is called another white box. So all the networks actually become fully mathematically explainable. And every layer, every operator has precise geometric or statistical meaning, right? Nothing you guess, right? It's really everything from the first principle. Now, any question? So this is an overall scope, right? Again, this is an overview of the course and the chapter 1. So we will have more dedicated lectures and chapters to study those things. We'll flesh them out later. Now, I wanted to converge a little bit, right? 1 second. Let me get a cup of water. Just 1 second. All right. All right, guys. So, yeah, I'm back. Sorry, it's a little bit dry throat. Speaking for 3 hours, so it's All right, so let's converge a little bit. All right, so we see there's a long history of people using explicit analytical models to model data distributions and to capture the low-dimensional structures, right? Linear, piecewise linear, sparse, low rank of massive high-dimensional data. And then in recent past 10 years, right, there's also a parallel. There's another history of people practicing neural networks, trying to emulating what's in our brain. And also in the past 10 years, is designing different neural network architectures to do learn data distributions, to do all this. They're all converging on really try to capture the low dimensional structure of massive data in high dimensional spaces. But nevertheless, right, there is always, you guys can see, right, this is not a picnic, right? Even people actually, there's a lot of twist in the story, right? In the beginning, people are always if you're a computer scientist, you know that when we grow up as a computer scientist, you know that we're always very afraid of high-dimensional problems, right? Why? There are many reasons, right? A lot of problems, they are computable, but they are NP hard, right? When the dimension gets high, you can see even seemingly very benign problem, like, finding a sparse linear regression becomes NP hard. It's NP hard to approximate, by the way, right? Once you get in the high dimensional space, a lot of problems become combinatorial. The complexity becomes exponential, grows in the dimension, right? And the scale become astronomical, right? For example, people try to solve chess or for Go, right? The state space is astronomical. The possible moves at each step is astronomical, right? So in the beginning, people are really scared. Actually, they call this curse of dimensionality, right? Even there's a history, barely 20 years ago, people don't even know, right? Solving linear set of linear equations in a high dimensional space, it seems to be intractable. Okay, that's a fact. Let alone say, right, and they have doubt about the deep networks can solve, right, can work, can solve those high dimensional classification recognition problems, right? Even analytical models, simple, seemingly ideal analytical models has trouble. How could But turns out the realization, but there's something in common about the first 10 years in the century about compressive sensing, and then later followed by the deep network. There's something very strange, very interesting. Suddenly people realize, right, in the compressive sensing, those high dimensional problem actually is not that scary after all, right? because there are things we don't understand about them, right? And yes, in the worst case, they're NP hard, but turns out as long as we add a little bit of benign condition, those problems become extremely tractable, right? Extremely, easy to solve, right? With, very minimal data, with very minimal computation, and has very scalable optimization algorithm, can solve those problems, guarantee accuracy and probability of success. All right? So it turns out they really the change from very pessimistic 从很悲观到非常的optimistic 变得很乐观，就是这是纯粹从理论分析。这压缩感知这一套问题解决线性方程稀疏线性方程的这个角度，从悲观变成了乐观这是但是完全是从纯数学从原理的方面来推导。那么接下来的10年，对不对 ？Then people start to practice in deep networks. Also, they see similar phenomena. Okay, again, right? Previously, they have a lot of doubt. 这玩意儿肯定不 work， 对不对 ？Because they don't understand. But turns out, the deep network demonstrate remarkable ability in dealing with those high-dimensional problems, right? AlphaGo or images, or long text, and so on and so forth. They can scale up very, very good. Very, very well, even leading to the so-called scaling law， 对不对？现在后来又叫做 scaling law。实际上，如果你知道前面10年发生了什么，所以 scaling law 对大家来说是一点 surprise 都没有。Okay, scaling law is just another derivative observation. Already there is a very good theoretical backup for that, right? In high-dimensional geometry, high-dimensional statistics, when the dimension is high enough, there's a lot of things that become very, very different. A lot of previously thinking impossible problems actually naturally become easy, actually become possible. We call it the blessing of high dimensionality, 对吧？这是在10几年前，在说大家开始意识到这些 practitioner 意识到 scaling law 之前，就已经有很好的、很严谨的理论的 justification。对。Hence, the situation becomes very, very different, 对吧？Then the question is, if we want to delve down a little bit down, right? Why? Question is why? 对吧？很多东西就是说对你自己观测到，对不对？但是这个压缩感知里面是，对吧？所以在这个高维统计、高维优化 the high-dimensional statistics, high-dimensional geometry, and high-dimensional optimization actually tells you why the good behavior of deep network is expected, because they're trying to realize compression, denoise, and operator in the high-dimensional spaces. They are pursuing the low-dimensional structures in high-dimensional spaces. Hence, all the nice properties that recovering sparse, low-dimensional structures in high-dimensional spaces, that deep networks, if you design them properly, they are also going to enjoy all the nice properties that this class of problem that admit. 就是这一类问题是可以解的。当你的神经网络设计，对吧？设计的神经网络正好在做这一类问题，也是在找这些地位结构，也是在实现类似的算子，去实现这样几个结构，那你就会 enjoy 这一类问题的好的性质，明白吗 ？Right. Then, at least for the analytical models, the sparse or low-rank structures, you actually can realize there is a rigorous reasons why they should work. Right? In the high-dimensional spaces, even the problem, if you can formulate the problem, relax the problem as a convex optimization, turns out that the algorithm can be extremely scalable. You can accelerate the first-order method, augmented Lagrangian method can enforce the constraints, low-dimensional constraints. Alternative minimization can make the scalability even higher. Those tricks are exactly used in the deep networks, implicitly or explicitly. Okay. Now, of course, the problem may not be convex, may not be linear, right? We know a lot of high-dimensional problems are not non-linear, non-convex. Turns out in high-dimensional spaces, long-convex optimization are very, very different from the long-convex optimization we encounter in low-dimensional spaces, right? Due to symmetry, stochastic gradient descent, generalized power iteration, turns out the long-convex optimization behaves, again, very differently in high-dimensional space than in the low-dimensional spaces. They have a very high probability converge to global minima, than the low dimensional problems, right? So those are the problems we start to beginning to understand, right? Why in high dimensional spaces, when you scale things up, the phenomena looks very, very rosy, very, very optimistic, very, very opposite to what we used to believe. 明白吗? Right? So this course, together with the high dimensional data analysis, will tell you guys why. We'll see later. Not only we're going to derive the network architecture, we'll also show you, right, even the object function associated with this kind of architecture, right? If you approximate those object function, those coding length, coding rate in a principal way, right? Those object function, if they are the natural measure of the coding length, the entropy of the data, 因为他们是选择很自然的，而不是瞎猜的这些 loss function. As long as those coding length, coding rate function has a physically or geometrically statistically meaningful, they're going to have extremely good behaviors. Their landscape is not the worst case that the people used to believe for long convex optimization. They're going to have a beautiful symmetry, beautiful geometry that have a very beautiful landscape, allows you to find the global or optimal solutions using simple gradient descent method. OK? 所以这些 realization 完全是就是非常非常 surprise 啊，所以这个就叫真是属于柳暗花明啊。这个过去这20年吧，大家对高维数据的这个处理分析和处理不管是从纯实践经验的 approach， 还是从理论的分析大家都发现，在高维空间中的这种低维结构，去寻找高维空间中数据中的低维结构这件事情完全是跟过去上个世纪的认识是完全180度反转的，非常非常有趣。So hence the past 20 years, right, of the century, right, the first 10 years are marked on the really sort of analytical approach to tackle the low dimensional structure in high dimensional spaces. The second 10 years, right, up to now, people are doing this empirically, right, try and error, throw a lot of compute, throw a lot of trials, a lot of teams, right, a lot of resource into it. Also discover the same phenomena, right? Hence, this is really like, as of today, we know this is a perfect storm, right? 为什么今天这个进展这么快，对不对？这个 scale things up，虽然这个很多 approach 也还是比较 brute force, but at least we start to enjoy the benefits, begin to enjoy the benefits of learning low dimensional structure in high dimensional spaces, right? And there is a confluence of advances in mathematics, the understanding of high dimensional statistics, geometry, and how to solve a seemingly impossible highly combinatorial problem, right? But they become possible. And also computation platform, right? We start to have cloud computing, GPU start to support massively parallel, distributed, scalable computing, and of course, the method, right? Computational method, convex optimization, first order algorithm, gradient descent, stochastic gradient descent, random sampling, which is behind the reinforced learning and deep networks, right? Which is approximating those operators, right? And they apply to big data, images, videos, text, everywhere, biomedical data, right? Really power all kinds of applications, right? So scientific discovery and also all kinds of practical applications. So that's really, we call it a perfect storm, right? 所以过去20年非常的 surprising， 非常 exciting。为什么？就不光是理论的突破，还有计算平台，还有计算方法，还有数据几件事情所以我们英文里面往往叫做 perfect storm， 对不对？完美的风暴往往是几件因素都达到一定临界点相辅相成，相互促进导致这个应用和进步技术上的进步层出不穷。So that's actually a recap of what happened in the past 8 years. Okay, that's the lecture for today. So we have probably a few minutes left. Again, I can take some questions and we can have some discussion.